We can proceed, right?
Right, you can go ahead. Thank you.
Okay, perfect. So the floor is yours.
Thanks a lot, Ignacio, for this nice introduction. Also, it's the first time I'm visiting Catalonia for work, actually. And it's as nice as visiting it as a tourist. So thanks for being a perfect guest, tolerating us for entire week and spending so much time. But I think we are making a good progress. Good. So today, I will address the question of how confusing exoplanetary data can be, and I would address them from the point of view of stellar physicists. Yeah, so whatever is first for someone, whatever is first for exoplanetary people is a blessing for stellar physics and for me. So that's what this all will be about. Let me very briefly present the team of people whose results I will be showing. So that's first of all lively stars group at the University of Graz, where we started basically 1 year ago. Still a number of co-conspirators at the Max Planck Institute for Solar System Forschung, and I will again talk a bit about their results. And it's also basically our bigger group of which we are working together with the ERC Synergy Grant. Hopefully next time there will be also many more results which come from our collaboration. Good. So the main topic is of our research over the last 10 years was basically solar-stellar connection. So what we can gain from studying the sun and stars simultaneously, yeah? What it means for us, yeah? That the sun is in principle the only star for which we can resolve time and spatial scales at which fundamental processes are going on. Yeah, so we can go and resolve, basically look at the sun with a very high precision at how gas is moving, yeah, at different heights of the sun. So we have tremendous amount of data. But still sun is just one star, yeah, with a given mass, metallicity of a given age, and also it's to some extent a very special star because it's the only star for which we detected a planet, yeah, with signs of habitability. Yeah, so this might somehow bias our selection and understanding of stars in general. Then for stars, of course, most of them, the vast majority of them is not even specially resolved. Yeah, so we don't have any information of what things are happening on their surfaces. But we still have a lot of exciting data. We still have a lot of exciting data. And overall, the line of research is how we combine what we learn, let's say, about general physics, about physics of atmospheres of stars, physics of the sun, from basically combining this data. And then, well, making some progress, hopefully both in solar and stellar physics. The idea is to also understand and improve our understanding of sun, Earth, and star-planet connection. And specifically, there are two main directions. Like first direction, which is mainly data-driven, it's how by observing many stars, we can learn something again about our sun. For example, a very important question of how typical is the sun as an active star, whether it's solar-like star at all, what was variability of the sun many billions years ago, and so on, yeah? Then second direction, which is mainly driven by segmentation faults. So that's basically, taking the code, numerical codes, which have been originally developed for the sun and extending into other stars, trying to learn more about other stars. And that's what I will mainly talk about today. And basically, trying to understand what we can actually learn about stars by studying various manifestations of their activity, and then how to distinguish these manifestations of activity from true signatures of exoplanets. But let me start now with the very, very beginning, like going probably 20 years ahead, 20 years in the past. So how the entire field, let's say, of solar activity, solar variability, started is, well, to some extent, I would say that is one of the most important plots done by Greg. So what we see here, it's measurements of total solar irradiance, yeah? And we see that total solar irradiance varies basically on all possible time scales. And in particular, there is a difference of roughly 1000 ppm, so 0.1%, from maximum to minimum. And when it was first measured, people got very, very excited, because they thought, how would this variability of the sun contribute to the climate change, to the natural climate change? And there have been a lot of speculations, like starting, from speculations that the sun could even contribute to the global warming, which, of course, now we know that, well, the sun is definitely not the driver of the global warming. But there have been a lot of speculations and a lot of attempts actually to understand what exactly we are seeing here. Why solar luminosity, basically why total solar radiance changes in time. And a lot of different hypotheses have been proposed. So now we sort of know the answer, and it sounds sort of, at least for some of us in the room who are in the field, sounds totally obvious, but like 20, 30 years ago, it was not. And people were speculating that actually the radius of the sun can change. That was actually a very influential paper of Jeff Kuhn, who speculated that the blackness of the sun can change and actually temperature distribution can change, like on the solar surface. And because, we don't need a lot to cause 1000 ppm variability. One can easily calculate that, I guess, quarter of a Kelvin would be sufficient. And there were basically dozens of papers claiming proposing various mechanisms for the variability. And none of them passed the test of time. As soon as more and more data appeared, we gradually learned, no, it's not change of the radius, it's not change of the effective temperature. We cannot explain the available data with this simple, with these mechanisms. And the only hypothesis which basically remains, and mechanism which sort of we now know causes the variability of the sun, at least on the time scales that have been observed, is basically trace variability of the sun to the magnitude. So we have magnetic field emerging on the surface and leading to the formation of different features. Dark spots, like here, or bright facula, and then the physics is as simple as it could be. We have something dark on the sun gets darker. We have something bright, the sun gets brighter. And that's basically, there have been a huge number of papers which basically show that we can explain with this hypothesis basically all available data. So that's sort of a summary of, let's say, our effort in understanding total solar radiance variability. What is plotted here, it's a power spectrum, wavelength power spectrum, that's why it looks so smooth, of solar brightness variations, total solar radiance, on time scales, depending from which area you are, you can either read in frequency. I cannot do it, so I would better read in periods and hours. So it's basically on time scales from minutes to decades. And here, two mechanisms have been combined. So first of all, on time scales larger than a day from somewhere here, these are magnetic variations. So in particular, on time scales of from days to months, variations due to spots, and on time scales longer than that, basically activity cycle time scales, variation due to bright features on the solar surface, which is called facula. And on shorter term time scale, that's basically was granulation. We will talk about it a bit more in a minute. So basically this bubbling, soft bubbling pattern on the solar surface, which is caused, by convective zone of the sun being just below the surface of the sun. Good. So our status is that we understand more or less variability of the sun. Now, it's obviously a good time to go and look at other stuff. And interestingly, to some extent, surprisingly, most of the, let's say, most fundamental results and discoveries in the field of stellar activity and variability obtained over the last 20 years have been obtained not with missions dedicated to study stars per se, but basically with missions which main goal was to detect and characterize exoplanets or their atmospheres, And, you see, the field, I would say, just skyrocketed over the last 10 years, Also advent of James Webb telescope brought, I will talk a little bit about that in the end of the talk if time allows, revolutionary results. So why is it so? Let me now, I think, animation comes and it takes a bit of time. Okay, now it's gone. So, when we want to study the Earth, we look at Earth. Yeah, when we want to study the Sun, we look at Sun. But we don't have such a luxury when we want to study exoplanets. So most of the exoplanets are not directly detectable. Yeah, they're just too weak objects too faint object in comparing to the stars they're orbiting. That's why to really study exoplanets, people usually look at stars they host. Yeah, and then, for example, the gravitational pull of the star might reveal the presence of the planet and also mass of the planet. Again, I will talk about it a bit more in a couple of minutes. Then, if you have, starlight being blocked by the planet, yeah, so we have planet which orbit a star in a plane of observer and the star, yeah. So we would from time to time see dips in the brightness of a star, and this can reveal radius of a star and also existence of atmosphere. And that's how basically, well, these are two main observables, two main methods with which exoplanets are being studied now. And there are three, let's say, most interesting for most of the exoplanetary astronomers directions and types of stars basically to study and types of exoplanets. Because I mean, obviously now everybody is very fascinated by the perspective of finding another habitable world or like biosignatures of another planets and so on. And there are sort of three directions, three most promising with the current instrumentation directions for that. First, well, it's observing and trying to find Earth twin around solar twin in the habitable zone. Yeah, so we need to focus on systems as close as Sun-Earth as possible. We don't have instrumentation to detect and study atmospheres of such planets, but just we know at least one system where it worked. Yeah, so obviously it would be very exciting to find a second system like that. Yeah. Then there are so-called cousins. So like basically it's Earths orbiting M dwarfs. And we already have a lot of them. That was already discovered many times. Well, many such Earths have been discovered. But the point is now try to detect the atmospheres. Well, and ultimately, which is already probably 2 steps ahead, compositions and hopefully biosignatures. So for this, we still have instrumentation. So that is what is within the reach of James Webb Telescope. So the critical part here, yeah, because these atmospheres are found basically by studying transits. Yeah, so the critical point here is the ratio between the radius of planet and radius of star. So for Earth rotating red dwarf, we have basically red dwarf being one area of the red dwarf is area of the planet is 100 times smaller than area of a star. And for the Earth-like system, it would be basically 10,000. Yeah, so it's not within, it's well above the limit of what, so well below the limit what now James Webb is capable of. There are also Earth nephews, which are potentially possible. Yeah, so it's like super Earths around G, K, and M dwarfs. Yeah, so then we have this factor of 1,000. And these three directions determine in a way, the groups of stars for which we now have most of the data for, yeah, because like when people were searching for Earth twins, they were focusing on stars very similar to the sun. When people try to understand atmospheres of rocky planets, they have been focusing on stars extremely different from the sun. And to some extent, again, this determines how we want to move and I mean, which discoveries have been made in the field of stellar physics. So let's now go step by step, yeah? So again, the message is that whatever group of stars we take, analysis is currently significantly hindered by the star itself, yeah? Because stars, unfortunately, they do not behave well. Now let's look at it a little bit more carefully. So let's start again with this Earth twin case. So the main technique is measuring the radial velocity of a star in the hope to detect these wobbles, basically sinusoidal wobbles, which are caused by the joint motion of a star or planet around the center mass. And the signal which we need to detect, for example, for another Earth would be an order of 10 centimeters per second. Yeah, so something like we should be able to detect Earth in a habitable zone of solar-like star, well, solar twin, let's call it. We need such a small level of a signal. And when we do measurement, imagine that we have absolutely fantastic instrument. Yeah, like we are not limited by the instrumentation whatsoever. So we now measure radio velocity of a star, but star is obviously not a stationary object. Yeah, so that's image from the deepest telescope of a rather large patch of the solar surface. Yeah, so we see that it's highly dynamic. Yeah, we have a lot of flows. So what now we actually have to do? We have to measure velocity of the center of mass of something like that. Yeah. And this individual velocities from this granulation pattern, what we're actually seeing, they're pretty large, 2-3 kilometers per second. So compare it now to this 10 centimeters per second we want to measure. Yeah. Now, obviously, it's not a net velocity. We have something goes up, we have something goes down, but it never averages each other. Yeah. So like for the sun, we have on its surface, on its visible surface at every moment of time, roughly 1 million of granules. If you now, think about signal from each individual granule, each individual patch here being on order of kilometers per second, we immediately find that the net signal, as soon as we are not in phase, it's basically on order of 1 meter per second. So still substantially larger than 10 centimeters per second limit. And this is actually now gradually getting absolutely critical. So I really like this plot. What is shown here, it's a plot from, I forgot to put credits, it's plot from Andrew Cameron. So what we see here now, it's an amplitude in meters per second of discovered exoplanets as a function of the year of discovery. So this point is a Nobel Prize of Meyer and Queloz. Yeah, so the velocity was roughly, I think, 60 meters per second. I cannot move that fast, obviously. Yes, it's as fast as you do it in a car, in a train, and so on. And then with time, engineers and astronomers, well, observational astronomers made a fantastic progress. So what is shown here is basically how accuracy of measurements improved with time. So somewhere in 2010, we reached the level of 1 meter per second one would naively expect from the sun. And then amazing thing happened. Instruments continue to improve. So what is shown here in blue is actually on-sky precision of available spectrometers. So we are now, they are now at the level of basically 10 centimeters per second needed to discover another Earth. But there are no discoveries. There are no discoveries. And, the limit of discoveries basically stopped exactly in this 1 meter per second. So that's a level we expect from a relatively quiet star. Yeah. So we now moved from the area of being photon or instrument limited to the area of being understanding limited. Because, we have a signal, but as of now, we don't know whether it's a star or it's a planet. Yeah, so because stellar signal overwhelms that of a planet. And, that sort of, in a way, I find it very motivating, let's say, for stellar physicists, for people who are doing modeling, because, well, observers made a fantastic job moving to the accuracy of 10 centimeters per second, which I cannot even imagine. That is something I would say beyond the comprehension. But we are doing such a sloppy, like theorists, doing such a sloppy job that we cannot really understand what is being measured. So that's sort of motivating for us to do a better job. And now, how we can sort out the issues? There are many different methods. There are many different ideas. I really like approach what Ignacy is developing. I will now talk about slightly different approach in my presentation stuff.
No, you can back and
probably I will do it like that. Sorry, I think I. Yep. Okay, let's do it. So how people are measuring radial velocity. Yeah, we have a couple of thousands of lines, and we look, well, how those lines are shifted. Yeah, so basically, how it's basically Doppler effect. Yeah, and most of the techniques until now to improve signal to noise were adding all the lines together. Yeah, basically, coming up with an average profile with different mathematical techniques, but basically it boils down to averaging many thousands of lines in one line and just trying to understand how it shifts. Yeah, and then start shift these lines much, much stronger. And one of the ideas of disentangling to effect comes from the point that planet and like planet-induced Doppler shift are line invariant. Yeah, we have the same Doppler signal, v over the speed of light. But stellar variability actually strongly depend on line. There are lines which are almost, there are no immune lines, but there are lines which are not that sensitive to activity, and there are lines which are very sensitive to activity. Sort of by mixing all this information together, by mixing all these lines together, we need sort of, we lose this invaluable information that basically there are two different modes of variability. And now, what do we need actually to have a proper scenario, to have a better technique for determining the velocity? We need to understand which lines are variable and which lines are less variable for a broad class of stars of interest. So the only way of doing it as of now, we can do it, of course, for the sun. Also, it's always nice to have some, prior information on which lines to look at, but it's very difficult to do it for all other stars of interest. So the way to do it is basically numerical simulations. And that's exactly where sort of we come into the picture with a generation of codes which have been already developed for many, many years. And now we are trying to extend them to understanding other stars. So basically, we have now machinery for simulating stellar signals from a broad class of stars. So it's based on radiative transfer and radiative MHD simulations, and a bit of flux emergence model. So let me now just show you how this machinery works. So we have now here beautiful image of a sunspot. And in reality, it's not actually, it's a sort of a trick. So here, there are simulations performed by Matthias Rempel, and here there are observations. And you can see how amazing the agreement is. Yeah, of course, when one goes to tiny details, there are always, the devil is in the detail, but at least on the first, we do, it's sort of a tremendous work how well observations are reproduced. So that's in a way a general scheme of what we are doing. So the simulations, they're called a so-called box in a star model. So we have our huge star, and we cannot simulate the star, as a whole. Yeah, so that is unfeasible now. I think there was very interesting estimate that, for example, to estimate the sun now, to calculate the entire sun now, we need a power to calculate 1 second of solar time. We will now need a power produced of a red dwarf within 1 second. Yeah, so that's this would be a bit too expensive and not that good for the climate, probably. We cannot really do it. Yeah, so that's why what we are doing, we take a small patch on a surface, we simulate this patch, but it should contain the most important physical scales. Yeah, so it should go below the surface where we have granulation, and it should go above the surface, where we have both granulation and radiative transfer. So basically photons are escaping from this area. Then we do radiative transfer on this cube and do basically get then something as beautiful as this, the spectrum. So we did, that's another way basically to illustrate how simulations work. So that's basically our cube when we change how it evolves with time. So we see very nice granulation pattern, which looks basically identical to what is observed. We see, for example, here in between granules, we have these bright patches. So this is magnetic field emerging in the cube. And that's what people usually call facula. So facula is basically, combination of many of these bright patches. Then a nice thing with simulation, of course, that we can do something what we cannot do with a real sun. Yeah, we can, for example, go a little bit inside the sun. So what is shown here, I think it's now. No, let me, oops. What is shown here is what would happen, like if we observe the sun in different locations within the spectral line. So here, this is image in continuum. This is image in continuum, and we see this beautiful granulation pattern. Then we start to move. We start to move from continuum to the disk center. Oh, sorry, to the line center. And you see picture changes. And then, for example, in the line center, we have this very interesting phenomenon which is called reverse granulation. Yeah. So while in the low photosphere, granules are bright, intergranules are dark, here things reverse. Yeah. So we have dark granules and bright intergranules, which has a lot of physical sense. I don't want now to go too much into the details. Then we basically took the simulations. Now we of course need to benchmark them. Yeah, we need to show that at least we can reproduce the sun. And over the next couple of plots, basically I will try to convince you that we can do it. So that's comparison of our calculated spectra with observed high resolution spectra and different mu angles. So that is disk center basically. This is a limb. This is some intermediate location. We can zoom in. And well, we can also reproduce quite nicely shapes of lines. So that was plot done by Somya, who was also visiting institute, but left a little bit earlier. Then, well, we can give all possible sorts of tests, like that we can reproduce limb darkening as a function of wavelengths, that we can reproduce absolute level of the solar irradiance, we can reproduce profiles of the individual spectral lines and p sectors. Yeah, I don't want to spend too much time on this. I just want, to demonstrate you that we did our homework and try to see, well, try to understand the stuff. And let me now show you a couple of results. So that's results by Florian, who is here in the room. I probably jumped a little bit ahead. Yeah, so basically what the message was that we tested our code against available data. Now we want to use this code to solve the problem, basically. You have to find the least and most sensitive lines to the magnetic activity. And here, that's sort of a basic experiment Florian did when we put a spatula on the star and let star rotate. What would be the radio velocity we measure? And this is basically the result. So we measure here radio velocity, it's line by line measurements. So what these curves show, how a radial velocity would look if we measure it in different lines. So we have iron 1 lines here, I think they're red. So red curves correspond to iron 1 lines and blue curves correspond to iron 2 lines. And the most important message from this plot is that these curves are not identical. That is exactly what we hope to find. So by measuring radio velocity in several lines, we get pretty different results. And we would not get it if we have a planet. So that's exactly basically the key what we want to find. We can now quantify, at least for the sun, and well, we're obviously now doing for many other stars. I mean, the next step is, of course, to test the simulations in the field and see how well they're working. But we can quantify sensitivity of lines to magnetic activity. Then another direction, another important direction was actually trying to quantify sensitivity of lines just to granulation, even if you do not have any magnetic field. Yeah, because, well, radio velocity people, when they search for planets, obviously they try to focus on the least active stars, which are only possible to have, yeah, not to be confused by magnetic activity. But even these least active stars, they would have, the granulation and all this bubbling pattern on the surfaces. So that's actually images, well, movies, they're a little bit stuck. Actually, they're running quite, oh, okay, now they're running again. So that's from Hinode in G band, so that is change molecular band somewhere in the blue area and in the green part of the spectrum. And we see this bubbling pattern. Now, calculating signals from these bubbling patterns would be extremely difficult because it would actually mean that to properly calculate it and calculate the contribution of granulation to spectral variability, we would need to run these simulations and radiative transfer for many, many hours and deal with a lot of systematic issues. So that appeared to be actually unfeasible task. And what appeared to be tremendously helpful here, it's a really funny property of the sun. So I'm now going a little bit into detail, which is probably not that important for the overall understanding of things, but I personally find it really fascinating and I like talking about it. So that's called ergodicity. What it actually means, that if you now take small area on the sun, and look, well, the movie is stuck again. Let me restart it. Not sure somehow. I think it's my computer is not okay. Now it's still moving. Well, now okay. It's a bit delayed. Good. So if you take a small patch on the sun and observe it for several days, observe it for several days, and we look how brightness in this patch of the sun would change, because that's sort of or how lines would shift, So this is basically the main properties we are searching for. So that's one approach. Second approach would be actually to stop the sun, and instead of looking at the evolution of this patch, look at how things would change when we move on the solar surface from patch to patch. And in principle, one can expect it from the stochastic process like granulation, but observations and also simulations show that the sun is tremendously ergodic. So it actually doesn't really matter what exactly we are doing. We're following it in time, or we're basically doing the spacing, which allowed us to cut the simulation times by at least, let's say, 2 orders of magnitude. So, and calculate many more stars, which would be feasible in any case, in other case. So that's some tests, basically, which prove that the sun is ergodic. I don't want to stop on that. I probably, will very briefly scan through the main results. So the point is that now also for granulation, we can quantify the lines. That's a work done by Somia. And well, we can also identify different modes of variability because some lines, their variability manifests itself as getting stronger or weaker with time. Some lines are actually dense, left and right in time. So one can try and go and quantify all these modes and then see what would be helpful. I think I will jump from that or through that. And now just show, our couple of just steps in going to other stars. So these are now simulations. Before I was just showing the sun, Now these are simulations for stars here on the upper panel with different metallicities. So here we have metal poor stars, the sun, metal rich star. And here we go basically from hotter stars, F3, down to M4. And one can see immediately that the granulation pattern changes tremendously. So specifically, these are plots done by Nadia, and what she did here, she kept absolutely the same colors here. So we can compare how surface looks at stars and at stars of different temperatures. So basically, you see that we don't see much on M dwarf anymore. So the granulation is getting much less vigorous, which is also, expected from general physics as well. Well, now just to show you what's going on really on M dwarfs, I changed the colors here. So then we can see the granulation pattern. We can also, go to even cooler stars and try to understand how magnetic activity of the stars would look. So that's basically, the picture simulations of the solar facula, disk center somewhere closer to the limb. This is the same picture of simulating facula for M4 dwarfs. Disk center somewhere to the limb, close to the limb. And well, that's what usually causes a lot of surprises, let's say, for solar physicists, because the feature which actually appears to be bright on our sun appears to be dark on cooler stars as M dwarfs. So that's probably, I would actually skip it. That's not that important now, but we can discuss it if needed. Then, well, one can also go and simulate spots on surfaces of other stars. So this is what we have for the sun, and then we go to orange dwarfs and red dwarfs, basically. and well, calculate the spectra. So simulations have been done by Tannenwirth, calculations of spectra have been done by Smitha. Well, people who are working with us. And well, one of the physical properties, what we see here when we go to cooler stars, that the contrast, a relative contrast of spots drops when we go from the sun to cooler stars. So we don't expect to have a really cool spots on red dwarf. Yeah, like for the sun, yeah, the spot is basically a red dwarf within the G dwarfs like the sun. But when we go to M dwarfs, the spots still look like a bit cooler M dwarfs actually. Yeah, so that's one of the properties of simulations, but it's very well agrees with available data. Now, let me jump now through many steps. So many steps. I was actually more or less sure, just in case I would be very fast. I added this couple of slides, and let me now go to the final part of my talk. Yeah. So now, just a short recap. We started with the sun. I showed you now a couple of stars going down to M4, and obviously the question which everybody, like from exoplanetary and even stellar community now asks, what about TRAPPIST-1, yeah? So TRAPPIST-1 is the red dwarf, yeah? So that's a cool red dwarf with a temperature of 2600 K with a number of rocky planets around it. And I don't remember, I think 4 or 3 of these rocky planets are within habitable zones, yeah? So that's basically the star which James Webb telescope observed now tremendous amount of time, and it's gets a little bit funny in a sense that we now know many properties of TRAPPIST-1, even better that we know that for the sun. Yeah, there are more observations, like for example, spectral white flares and so on. Yeah, so you can model TRAPPIST-1. Now the question is, do our simulations really represent what happens on TRAPPIST-1? And honestly, I'm not that sure. Because everything what had been done until now, we have been basically modeling effect of magnetic field, effect of Lorentz force on the convection. On TRAPPIST, many other processes can take place, yeah, because it's such a superactive star. We have flares, we have, well, a lot of physics which we never dealt with. Yeah, we also have pretty low electron concentration. Yeah, something we never dealt with understanding the sun. So the answer is we can get possibly spots, we can get possibly facula, whether these are features which are actually in charge of what TRAPPIST-1 is showing. I'm skeptical about that. Yeah, so, but the funny point, we still can have a lot of fun with TRAPPIST-1 just based on our general understanding of physics, and again, a couple of lessons learned from the sun. Let me now show you just a couple of, well, 2 slides basically. So first, I think I still have a couple of minutes, right? Not very sure. Okay, good. So, even 5, perfect. That's, I think, exactly what I need. So, flares. We know that the temperature of white light, solar flares, is about 9,000 Kelvin. And so these are basically temperature measured in the visible range. Yeah, now not talking about, well, usually what people usually associate with UV flares and coronal mass ejections, whatever, that can be super hot. But white light flares, whatever we see in the visible, it's roughly 9,000 K. And this number has been widely adopted in stellar physics. Yeah, because for example, when analyzing Kepler data, or test data, flares in Kepler or test data, because Kepler observes in some passband. And what usually people are interested in, we need to know to the total energy, yeah? How we go from this passband to the total energy. We need to assume some energy distribution, yeah? And this was widely done, assuming this 9,000 K we learned from the sun. But then first, GVST observations immediately show that the temperature of white light flares on TRAPPIST is very different, 3,500 K. And that's amazingly, like if you look at many flares, it's basically sort of limit at which it stops, well, immediately after the explosive phase. Yeah, I'm not that now interested in explosive phase, but it's a temperature of what we would observe, let's say 1-2 minutes after the explosion, when energy penetrates into the photosphere of TRAPPIST-1. And this, even so, we cannot model it. Or, we can, I just don't know how good it will be. this, whatever instrumentations I show, we can now look at the very basic physics. Why we are now, like again, it was obvious like 30, 40 years ago, but people already modelers start to forget that why actually we have this 9,000 K for the sun. And the basic physics is very simple. So as soon as we reach 9,000, hydrogen starts to be ionized. Yes, hydrogen starts to be ionized, and it's basically it works as a sink of energy. Yeah, we cannot. It's very difficult to heat it above 9,000 K, like water. Yeah, when we heat water, we reach 100 K, 100 Celsius. Sorry, then transition starts. Difficult to reach it further. The same was for the sun. That's basically the fundamental physics of 9,000 K. But of course, over time, modeling progresses tremendously. We go out of statistical equilibrium, so on. But that is basic physics. And now, what do you think might happen on the TRAPPIST-1? We don't have too much of hydrogen in neutral form, but we have molecular hydrogen. And what is shown basically on this plot is how a relative concentration of molecular and neutral hydrogen changes with temperature. So when we sit at the low temperature, everything is in molecular phase. We shift the temperature a little bit, and then this transition, that's sort of the most important part, happens very, very abruptly. So that's a property of Saha equation, or this analog of this equation for molecules. The same, when we go from neutral hydrogen to the ionized hydrogen, it happens very, very abruptly. And if we simply differentiate this curve, we can get something like a heat capacity. And this heat capacity would have two maxima. First corresponding here, it's a little bit higher than this 9,000 K because calculations are performed for the pressure on the surface of TRAPPIST-1. I mean, molecular equations slightly depend here on pressure equilibrium equation. But we can nicely have this peak at about 3,500 K. So that's sort of what I, in a way, like. Okay, we don't understand nitty-gritty, we don't understand, we cannot do, let's say, full-scale modeling, but again, using, in a way, the solar approach in basic physics learned from the sun, we can start explaining things. And let me, well, I'm not showing that, let me go through the final example. Let's look at flares. Let's look at, that's a work done by Valery Vasilyev. For whatever reason, I didn't put his photo here. So let's look here at flux of TRAPPIST-1 during the flare. So that's what is shown here. Yeah, we have flux, boom, flare. Then we have this very annoying transit. And then flux actually returns to the level higher than it used to be before the flare. And that's very, very persistent. So Valery analyzed as much data as he could. And he always saw, yeah, there is this offset. Flux never returns to the level it used to be. What's the reason for that? Yeah, there might be, and we never seen it, we never saw it for the sample. Yeah, so there might be many different explanations. But again, one explanation might be prompted by solar high observations with high spatial resolution. So if you now take a spot, that's a now solar image. You take a spot which corresponds to the flaring event. So this is a spot pre-flare, this is a spot after flare. And what actually happens? It's a little bit, you need to be a little bit of imagination. Like for telephysicists, probably this picture would look extremely boring because it's a tiny detail. For solar physicists, it would look much more exciting. But what actually happens is dedicated, it's shown here in this blue color. What happens is after the flare, small part of active region disappears. Yeah, so we have a reconfiguration of the magnetic field, and small part of the active region disappears. And now, on the sun, we would never see it in the disintegrated line because too many things are happening. Yeah, and generally the size of the disks of the spots is not that large on the sun. But now, if you do an exercise and zoom in, we integrate now flux only within this image. Yeah, forgetting about everything what happens outside. Then we would actually see very similar offset. So the flux starts here, jumps, and then it never returns to the same level. Yeah, so for a long period of time, it's a little bit higher, which is simply because part of the dark spot, well, in this case, penumbra, actually is gone. And we believe, well, at least it's reasonable to assume, we don't have any other reasonable proof, of course. We believe that it's exactly what is happening on TRAPPIST-1, just on a much bigger scale. And the funny thing of it, that with this we can now go and measure the spectrum of whatever thing is disappearing. Yeah, we now look at the deficit of flux as a function of wavelengths, and it directly gives us a spectrum of the feature what disappeared. And these are 4 spectra for different features. I mean, the accuracy is obviously not, signal to noise is not that high, so it's difficult to say, well, to find any specific bands here. But what it is interesting. The spectrum of this feature does not correspond to a much cooler region than the spectrum of TRAPPIST-1 itself, because to explain TRAPPIST-1 data, a lot of interesting hypotheses have been proposed, like it's populated by features which are, let's say, 600-700 cooler than the TRAPPIST-1 itself. Here we don't see it. So whatever disappears is just slightly cooler than the TRAPPIST-1, like 100 200 or whatever. Funny enough, this might be consistent with the temperature of spots on TRAPPIST-1. We might get, I'm now jumping a bit ahead. We don't yet have true simulation, so we stop at M4, but if we now continue as a trend, we might expect that it would actually correspond to something we can get in TRAPPIST. So what I wanted to show with these 2 examples, again, that's sort of what really keeps me excited. Also about the direction of stars, the direction of stars for which we have very little understanding, which are very different from the sun, and just blind usage of all the machinery we have been developing, let's say, for sun-like stars is probably not the best strategy. We still, based on, very general knowledge learned from the sun, we can learn a lot about the stars. So that's, I think, I will conclude with that. So despite all we are sort of in the very beginning of our trip in understanding what actually exoplanet observers found. But I believe that despite all the segmentation faults, we are moving to something bright and exciting. Thank you.
Cool. Thanks very much, Sasha. We have time for some questions. Brief. Yeah. Go ahead.
Thank you for the talk. If I understand correctly, when you mentioned the stellar motion will change, will have lead to the Doppler shift for the lines, and when you move to the what's that? The facula. The facula will have the change also the line intensity and slightly about their central energy.
Yes.
How can you distinguish these line? What's that? The planet's motion and the facula change for the line change in the line centers. I'm just curious. Can we distinguish that? Or
I hope so. Well, I'm very much convinced so, actually. And again, the key is, let's now talk about let's give a very simple example. Imagine that we have a group of lines which is not sensitive to facula. And then we have a group of lines which is very sensitive to facula. We measure the signal in these 2 groups. If it's facula, we have 0 in one case, we have signal in another case. If it's planet, all lines are equally sensitive. So we will always see absolutely the same signal. Or, like in a more realistic case, as soon as we have different signals in different lines, that might point to activity, as soon as, of course, all other effects, instrumental effects are taken into account. So the key is, at least from what I have been showing and from the direction we have been pursuing until now, the key is differential line-to-line sensitivity, which is not the case for planetary signals.
More questions?
For the TRAPPIST-1 pre and post-clear flux offset that you're observing, especially given that the cool star and therefore a very cool spot or region of low temperature change, you can directly determine the area of it from that. So now what fraction of the star surface is lost by that flux change?
That's exactly shown here. That's exactly, let me just show it. So that's what, I mean, that's estimation for this post spectra which are shown here. That's what is lost. It's not entire area of the region, but it's exactly what is lost. And here, well, but the circles have slightly different radii, depends a little bit on assumptions that are put there. So it is visible. It is visible.
But that's a size picture, scale picture.
Yeah,
of the
scale,
areas
scale.
that are lost.
Exactly. Of these 4 regions which correspond to this four spectra, to this formation spectra. So I don't remember the numbers. Well, it looks to me like 100, probably, yeah. So it's quite a bit. It's quite a bit, but TRAPPIST is, you know, the funny point is that if you now look at the energy distribution of frequency occurrence as a function of energy, it would be the same for TRAPPIST and for the sun. Even so, the sun is well, much bigger and much more luminous. Yeah, so like the same flare, what we see, the same energy, what we see on the sun is obviously tremendous in the scale of TRAPPIST. So the point is, yeah, there's a much more violent processes than what we are used to.
But if those are only the lost regions, they presumably came from much bigger regions.
Oh, absolutely. Well, I mean, in principle, yes. In principle, yes. On the other hand, well, you see, we don't really know what it is. Might be umbral dots, it might be spot. I mean, on the sun, there have been, it's mainly penumbra which disappears, yeah? Also, there have been reports of small spots disappearing, yeah? So yes, this might be, I mean, we don't know whether it's a part of our entire region which is crushed. But at least, you know, it shouldn't be smaller than that, yeah? So that's at least what we know for sure.
Okay, more questions for Sasha? Yeah, they're on the back. Yeah, I don't know.
Okay, great. So I have maybe from the distance I cannot see clearly that but maybe it's a question. So 2 of them. So one is when you were showing this pre and after post birth. So if I understand correctly, yeah, the other side, the one is so in the post birth, there is more penumbra, right? So there is more region, and then it could be failure.
So penumbra is gone. Penumbra is gone. Part of the penumbra is gone, basically. Look here. Like, I mean, okay, let's not look at this forward plot.
The top left is pre-birth.
This is pre-flare, this is post-flare. And basically what happens, small part of the penumbra is gone. It's here.
Okay, yeah, because I was checking the center, there are some parts where there was not penumbra, but then there is penumbra.
Yeah. Well, I mean, so that's basically attempt to make the difference. I mean, the effect is not huge. Yeah, it's something what would not, you know, strike you immediately, but it happens. So, I mean, we know that, like you see, what is, in a way, the philosophy of it. We could immediately come up, I mean, it sort of sounds natural. Flare happens, a reconfiguration of the magnetic field, something should be gone, yeah? Whether it's our fantasy or not, the sun provides us a very good laboratory basically to check. So the effect is physically possible, yeah? That's sort of what we try to achieve here, even so, you know, the image is probably not the most exciting one, yeah?
And the other question that I had is in relation to the change of the intensity for the different lines. So what is the reason behind that? So it's related to the expression of the different conditions that we're observing and then the temperature of the fractal you're observing?
Yes, actually, that's one of the very important. So excitation, because you're now talking about different sensitivity of lines to focal transit, yeah? So 2 things. First of all, it's formation, it's a depth of formation of lines, yeah? Because lines are formed at different depths, and then we have basically slightly different dynamic, yeah, in the atmosphere. But then what you mentioned is actually an effect which is extremely often ignored, but it's absolutely critical. So even if you have 2 lines which are formed in absolutely the same level, but with different excitation energy, the sensitivity to the change to convection is very, very different. That's why actually, you know, what I was showing, we see very different patterns in iron 1 and iron 2, for example. So, and that is, well, basically it's a Ha equation.
Yeah.
So Boltzmann did that, but yeah.
Thanks.
Any further questions? Yeah, please.
Great talk, thank you. Just to follow up on this, what would be the operational challenge of doing this high resolution spectroscopy during transits that were previously identified to eventually discover outlines, right? Where are you in terms of observation in this project?
Well, it's mainly probably question. I mean, Ignacy in much better position to answer than I. You mean now, are you referring to RV or to photometry or like photometry? Well, observational challenge. So you know what? Let's go step by step. So number of things can be already tested. For example, like limb darkening of a star, yeah? And we know that we can reproduce it very well and we see magnetic effects, yeah? Now, when we talk about photometric signal, well, the observational challenge is to have a good signal to noise at different wavelengths, because I mean, the key is again, like in RV, it was line-to-line sensitivity. Here, this is dependence of the signal of the wavelengths. Yeah, so the key is to get good signal to noise and see basically whether we can reproduce reality or not. If this is.
So have you already saw like line painting during your 20s? With the and you know comparing iron 1 and iron 2, and you see changes corresponding to that.
So here, when we talk about lines, it's mainly applicable. One can do what is called Rosita-McLaughlin effect. Yeah, so when a planet is transiting a star, we look at high-resolution spectra. Here it was slightly different. So basically, we look at the sun for a couple of hours, or the star, even outside of the transit. So transits are not essential here, yeah? And we try to see how lines are sensitive to granulation, yeah? We don't have a proof. We don't have a proof. We know that lines are very differentially sensitive, but that's one of the reasons, actually, while we are here to see whether our predictions are working for the sun and for other stars, yeah? That's basically one of the things we have been discussing here for days. Like if you provide sample of lines, which are supposed to be the most sensitive, and sample of lines, which is least sensitive. Can Ignatievich and his group with his data prove that this is what we see? So that's, we are not yet there. We are not yet there, but next time.
So next visit. Any additional question? Maybe you can ask, is there any question online? If so, please speak up. Okay. Fairly quiet. So it's 1:03. It's perfect time for pizza, I guess. So we can move downstairs, and please wait for the speaker before eating all the pizza. All right. Thank you so much.
How we can remove this configuration.
Yes, exactly. Useful. Yes. So we'll take. Thank you very much.
Now it's time to